find out which paragraphs on page 21 best mentions the gaps of the spaces found on this page, page 23. What? Jake is here. Hold on. Where's Brian?
Oh, he's not here. Is it not here? No, you're looking. Yeah, Brian's not here.
Hey, what the? Huh?
What?
Okay, so Brian's not here.
Brian's there.
Yeah. Hey, you were here a moment ago. Okay, today, a few things we are doing. First thing, we'll do a recap from yesterday. Second, we're going to look at the kinetic particle theory in relation to temperature. Let's begin with a quick recap. Yesterday, we looked at an experiment conducted by Robert Brown. And Robert Brown observed a very interesting form of movement, which he named after himself, the Brownian motion. If someone were to explain in words what exactly the Brownian motion is, it is this jerky, random movement that you observe if you put very small particles, stretch that, very small objects into liquid or gas. For example, if you were to put pollen on a drop of water, or if you were to put dust into air, you would observe this jerky random movement, and we describe this movement as Brownian motion. This motion is very useful to justify and use as evidence for why we think that the particles of liquid and gas are actually in motion, in movement. By itself, you may think that these pollen grains or dust are alive because they are moving by themselves. You may even think it's because wind is blowing and they are moving. But in reality, they are moving because of all the liquid or air or gas particles bumping into it from various different angles. Because it bumps and collides at various angles at different speeds, their movement looks very irregular. If I were to trace the path, we will see that their movement doesn't even take a very focused direction. They're just moving almost anywhere. That's because the way the liquid or gas particles are bumping into them is very random. That being said, if I were to put pollen grain or dust onto a piece of solid, would you observe Brownian motion? Okay? For example, if I put pollen grain on a ruler, now you just have one ruler, then just put a little bit of pollen grain at the tip of it. Will you observe the pollen grain moving? Okay, Para says, when you look at a ruler, the particles of the ruler are very closely packed. And we know for a fact that they are closely packed, at the same time they are vibrating about fixed positions. Could that cause the pollen grains to also move above it? So the answer is no. Actually, these minute vibrations about their fixed positions, they are not strong enough to cause polar grains move. Polar grains is actually many times bigger than any one of these ruler atoms. So, what am I trying to say? You can only observe Brownian motion if you put things in liquid or gas. You want to observe it in solids. Okay, you want to put any on solid. I put my marker on this table. You also will not see the marker moving.
It's moving.
No, it's not moving, it's the wind. Okay. You will not observe the marker moving because even though the atoms, the particles of this cable is vibrating on the spot, it's not strong enough. Okay? If not, you standing on this floor right now, you will feel the floor rumbling all the time, right? But we don't. So you only observe this in liquids and gases, and only if the object is small enough. I mean, if I were to jump into a puddle of water, it's not like you can feel yourself vibrating on the spot, right? Or moving in the water. You don't. So the object needs to be small enough, and you need to put it in liquid or gas. Put it on anything solid, you won't observe this happening. So please take note. You write this somewhere in your notes, Brownian motion, you can only observe it. You put something small in gas or liquid. And we use it as evidence that liquid and gases, they are moving, not about fixed positions. They actually slide across each other, bump into each other. Okay, so I'll give you some time to jot down what was said, what was discussed in class. In a while, we're going to go through checkpoint 1. Which paragraphs best describes these properties you see on the screen? Check you can catch up by watching our lesson recording. Okay, so a quick recap. Previously, I told you to number off these points as A1, A2, A3, B1, B2, B3, C1, C2, C3. Then you are asked to match them according to checkpoint 1. So let's look at checkpoint 1. Yesterday, for checkpoint 1, these are the best paragraphs you can fit to explain the phenomena. Let's look at the next part. You want to check with your friends first, have a quick buzz, see if you chose the same paragraphs or there's something different. Like buzz as in talk, like not between each other. If you want to double check, have a look at your points. Okay, let's go through. So, how will you explain why solids have a fixed volume, liquids have a fixed volume, gas have no fixed volume? Volume has to do a little bit with whether things can be compressed, right? If you can compress something, you find that the volume can change. You make the volume smaller. For example, gases, according to primary school, can be compressed. Liquids and solids not much so. So which one will best explain? I believe it's a mixture of a few points. Number 1, particles are closely packed in fixed position, held by strong forces of attraction. Notice it's quite similar to the first description. So which points best match? If you compare, I believe it looks almost the same. Okay, particles, fixed positions held together by very strong forces. Let's look at volume. Particles closely packed in fixed position held by very strong forces of attraction. Okay, it is almost essentially the same. So that means it's a combination of a few points. Okay, so which ones are you using? Closely packed fixed positions held together very strong forces of attraction. So this one you have to use the one that talks about arrangement, about the movement, as well as the strong force of attraction. Okay, so I think the two that you need to combine are likely the A's. Yeah, you have the A's with you. Ryan. Okay, do you put down the A's? Okay, other than the A's, I think in this particular one, you may want to choose the B's. Right? So for this point over here, do you put all the A's and the B's? Because whether you can compress or not depends on how closely packed they are, how much space there is in between. What was yesterday's one? The first column, the first row. There was A, is it? A, is it? There's A1 as well as C. Okay, let's go to the next one. So what about high density? Density means how much mass can you fit in 1 unit of volume. So the more mass you can put into the volume, the higher the density. That will also mean that the closer the particles are, the higher the density also. For example, if I compare this highly packed versus the same volume but the mass is less, which one will have a higher density? Okay? So, very closely packed, spread far apart from each other. Which description best matches this? Sorry? Yeah, I think the B's best represent this, because the B's represent that they are very closely packed. Yeah? Okay, the B's describe the arrangement, how closely packed they are or far apart they are. Last one. Solids cannot be compressed, liquids cannot be compressed, gases can be compressed. Okay? What will best explain this? Okay, it has to do also with how closely packed they are. So I think again, the arrangement best describes it. I think perhaps what is lacking that you can also add in, so you can add it for yourself, that may not be in the full description, is that they included therefore that there is very little space between the particles. Okay, other than it being very closely packed. Very little space between the particles. for yourself. Do get familiar with all this. You are expected to know this. And it helps to explain a lot of the phenomena. Okay, today we're going to look at the kinetic particle theory in relation to temperature. So I believe you can flip the subsequent pages. Okay, so your page 23 should be done. Now let's go to page 24 and 25. Then it's our scope for today. I will need you in a while's time to have your iPad with you, because I'd like you to scan a particular simulation that you can play with. I'd like to hear your observations as you play this simulation. Okay, just a show of hands. In primary school, your teacher, science teacher, teach you about energy? Okay, so other than kinetic energy, can you name me other energies you know of? Okay, I heard of potential energy. Hear before? Primary school taught you. Okay, so there's potential energy. Any other energy? Oh, elastic. Okay. I think the full term is elastic potential energy. Any other energy you learned before in primary school? Haven't? Gravitational, thank you. So there's gravitational. Okay. Is there a gravitational energy? Yeah, there's a missing, thank you, Shivani. Gravitational potential energy. Anything else? Chemical potential, okay, I didn't be lazy, I'm going to write chemical here. Potential energy got many kinds. Any other forms of energy? Light. Okay, so light energy. Olivia, you want to say something? Okay. Kara, what did you say? Heat energy. Okay, so I want to clarify. When you come to the JC level, we don't refer to it as heat energy anymore. We refer to it as, goodness, just change the marker and after looking. We refer to it as thermal energy. Thermal referring to like temperature. Like, have you heard the word thermal before? Like thermal flux. Yeah, so thermal energy. Do not use the word heat energy. Okay, heat energy is not correct. We use heat in the JC level more like your LA teacher teach you what verb is action, right? Action word, right? Action word. Okay? Heat. So for example, I can heat something up. I put you in the oven. You are heating up. Okay, but you are gaining thermal energy. Okay, so heating in a JC level, we use it as a verb, a process. Okay? Instead, use thermal energy, not heat energy. Okay, so you know quite a lot of forms of energy. For this particular chapter, I'd like you to focus on one particular kind of energy, or a few of them. Number one, kinetic energy. I'd like you to focus on. Other than kinetic energy, I'd like you to also focus on thermal energy, which what you learned before in primary school as heat energy. Okay, but I'd like you to change the way you describe that. Okay, so two things, thermal energy and kinetic energy. We're going to find out how they relate to each other. First and foremost, we'll do a quick recap of some things that you may have learned in primary school before. Okay, I don't know in primary school you all learned that kinetic energy got equation. No? Okay. Then I wait for your JH3 physics teacher to teach you. Could I what is kinetic energy to you? Okay, Kara says she thinks kinetic energy is the energy that causes movement. Yeah, well, in other words, you could say it that way. Kinetic energy is the energy of movement. When we look at light energy, there's a different form of energy. But every time we talk about something having kinetic energy, we know that this thing is moving. The more kinetic energy you have, the more movement. There are two relationships that I'd like you to absorb. The first one is, the bigger you are, the more kinetic energy you likely have. For example, if I were to take a very small ball versus the big one, and I were to bounce them, comparing these two, the bigger ball will have more kinetic energy because it has more mass. The bigger you are, the more kinetic energy. Imagine now, if I were to take these two balls, the small and the big one, and throw to your face, and you didn't have time to react, which one will hurt a lot more? Prefer the big one, right? Because the big one has more kinetic energy. The bigger the mass, the more painful.
Okay, but then there's also the what if the ball is smaller?
Fair enough. Okay, then Jack brings in another point. But this ball is smaller. It could also mean I can throw it with greater speed. Okay, so if I were to take the small one and throw it at greater speed, so I'm going to represent this. I'm going to represent the size of the arrow as the speed. Okay? Oh, wait, it should be more, right? Have you ever seen something first?
But like, even if the ball is bigger, the amount of mass may not be bigger.
Oh, that's fair enough. Okay, so an assumption I'm making here, that these two balls made of same material. Ken, is that okay, Evan? If it's same material. But thanks for bringing that up. If this is like a hollow ball, then this one is made of metal, right? Confirm it's going to hit your face more painful, right? Okay, so number one, let me draw two different scenarios. Small one, small ball, big ball. Okay, then one more. Maybe I add in the units, then you all can be a bit more convinced. Okay, I throw something as 5 kg in your face. Okay, so supposing I throw this small ball accidentally in your face with this much speed. Okay, yeah, accident. So I throw it with this much speed. The big one I also throw with this much speed. Overall, which one will have a greater kinetic energy? The bigger one. The more mass you have, all else things, everything else kept the same, this one would have a greater kinetic energy. However, technically, if I were to throw this with less speed, and then this one wow. Okay, I throw with very, very high speed. Like a bullet. To be fair, if you look at a bullet, the bullet's mass is very small, but its speed extremely high. This one over here, the kinetic energy, will also be affected. So two things affects the amount of kinetic energy an object has. Its speed, how fast it goes. Number two, its mass. So thank you Jack, that you brought up that actually something small could also hurt you if I throw it at high speeds. But the mass actually is not that high. So, how do I optimize the person's pain in the face?
Why does it
Make it pointy, so the impact area is smaller.
Make what?
Make it pointy, so the impact area is smaller.
Okay, sorry, okay, I mean if I just keep to these two balls, yeah, cannot modify it. Don't throw it. Okay, I'll tell you how you train your arms so that you can throw this 5 kg one at high speed also. Yeah? No, this one I want to smash the whole face one. Okay? Okay? So two things that can affect speed, can affect kinetic energy. You also find therefore, I'm bigger than most of you all, some of you are very small size. If both of us were to run on the track, right? Then at the last part of the track, both of us need to stop, right? I'm going to have a greater problem stopping because I have greater mass. But supposing you run at the same speed. Okay? The unit for energy is joules. This word joules. Joules. Okay? Or the symbol is J. So may I get you to, I think in your textbook, you may not have written the unit for energy. So the very top, 8.5.1, they put 8.5.1 and they put kinetic energy. Could you just write down that the unit is joules? Speaking of balls hitting faces, last time I had a very unlucky streak. Every time I sit near a football match, the ball will hit my face. Like hit on, spectacles will shatter.
Then hold your eye, hold it.
Yeah. Any match that involves balls, if I sit nearby, it will hit my face. So I remember in primary school, but the first time the ball hit my face, I asked for it. So you know those like primary school, you have like those cages, and after that inside the cage, it's like street soccer match, right? So there's a football court, then these are fences, then after that they have goalposts like that. Okay, then a bunch of senior boys were playing inside the court. Then I wanted to watch them, so I pressed my face against the fence over here at the goalpost. So I was watching, very exciting. I want to see the ball come towards the goalpost. So I put my face literally at the back of the goalpost, at the fence. So I watched. Someone scored a goal really hard. So they scored a goal, literally in my face out. So that's the first time I remember. Second time, so I learned my lesson second time. Second time I didn't even sit at any of the fences. I climbed up a hill, sit on the second floor, watch the football match. Yeah. Watch the football match. Watch. I talked to my friend, next thing I knew the ball came from downstairs to the second floor, hit my face. Yeah. The third time, I thought I'm giving up on soccer, not going to watch anymore. I'm going to watch a basketball match. So I went to watch the basketball match. I thought to myself, as long as I don't be at the goalpost, I should be safe, right? So I stand at the side this time. Not at the second level, just at the side, just watching happily. Wow, this one pop hit my face, then my specs came off, right? Broke into two.
Have you ever been to a hockey match?
No, that will probably lose my teeth. Okay, but that's because they threw the balls with high speed and it was high mass. Often lose my teeth. Okay, so we learned that big objects have kinetic energy. But what about the particles of the objects? It's the same thing. If we look at any object, for example, any one of these balls over here, if we were to zoom in, even though they are in their solid state, they also possess kinetic energy. Not as much because they are vibrating about their fixed positions. But if we compare between solid liquids and gases, we find that liquid state has more kinetic energy versus gaseous state. So, if I were to go back and bring you back to this simulation over here, a few days back, we used this simulation. I want you to observe how fast the particles of solid, liquid, and gas are moving. So you look over here, this is solid. Now let's go to liquid state. Notice that the particles, although the mass has not changed, same amount of particles, each particle also same mass, we see that they are moving faster, the speed is faster. That means their kinetic energy individually has gone up. If I go to gaseous state, we find that gaseous state, all the particles have much higher kinetic energy because they're moving very fast. What this means for you as a student is, actually the way we convert between one state to another is to increase the kinetic energy of the particles. The faster the particles can move, the faster the particles can move, the more they will convert from one state to another. Okay, then you can ask, okay, but does that mean if I slap the table enough, eventually this table will get very hot? Then that begs the question, how in the world do we supply kinetic energy to the particles in the table? Yeah. If you go YouTube and search, there's one guy that tried to slap a piece of chicken to see if the chicken's temperature can increase. It doesn't really work. The way to increase the kinetic energy of these solid particles is to, that's why we are learning, that's why I wanted you to bring in thermal energy again. The best way to supply particles with kinetic energy is to supply it with thermal energy. You learn in primary school energy can convert from one form to another. If you were to supply thermal energy to the particles, okay, I'm supplying thermal energy now. Notice that the thermal energy is converted to kinetic energy. Every particle is starting to move faster and faster and faster. This is how thermal energy and kinetic energy is related. The more thermal energy I supply, the faster the particles move, the greater the kinetic energy they have. So don't go around slapping people's face very fast. It's not going to get them to heat up. Instead, put a candle to their face. Yeah, I feel like I'm teaching very wrong things. Then later you'll crop me out of context. Right? Then put a... Okay? So this is a relationship. I'd like everyone now to try out this particular simulation. You may take your iPad to scan this. This simulation will bring you to a page that shows you a bunch of particles that you can add thermal energy to. I want you to observe what happens with the more thermal energy you add to the system. Okay? Very good. Once you're in, yes, I would like you to spend. Go and add as much thermal energy as you can. See what happens as you add more thermal energy. Yeah, I can show you the code again. What happens? What do you notice when you add more thermal energy? That's my first question to you. What happens when the particles gain thermal energy? Okay? Next thing that you can try. How many of you has already maxed out the thermal energy? Show of hands. Okay, if you have not maxed out the thermal energy yet, could you do me a favor? Go and add as much thermal energy as you can. Add. Until the button don't let you add anymore. Okay, done? What happens when you add more thermal energy? There are other measurements provided in this simulation. What happens when you add more thermal energy into the system? You ready? I'm going to ask some of you. Vera, what happens when you add more thermal energy to the system? What do you observe? Okay, Vera observes that when you add more thermal energy into the system, the particles move faster. Why do they move faster? Let's go one step back. Why do they move faster? Evie, why do they move faster? Sorry? There's more? Okay? EV says, well, the particles are moving faster because there's more kinetic energy. Yeah, right. Right, okay. Because you are heating up this system. As you heat up the system, you are giving more thermal energy. And as you heat it up more, the particles move faster because they also have more kinetic energy as you heat it up. Okay, so that's one observation you can make. What about the temperature? What do you notice about the temperature as you increase the thermal energy? The temperature increases, yeah? Okay, now I'd like you to try something. After you have maxed out the thermal energy, could you try this? After you max out the thermal energy, I want you to press the stop button. Do you see a stop button on your screen? Have you stopped it? And it's the temperature at its max? Okay, now I'd like you to try this. After you stopped it, can you start to add particles into the system? You see all these blank spaces? Actually, if you were to tap the blank spaces, more particles will appear. Could you add as many particles as possible? And tell me what happened. Tell me what you observe when you add more and more particles. What do you observe when you add more and more and more particles into the system? It slows down? I think you need to one by one. Oh, it's not detecting. Oh. Yours doesn't seem to be detecting its bigger. Stop it. Yeah, it doesn't seem to be detecting. No more space? They're a funny bunch. Every time I give you a simulation, you will find new ways to break the simulation. Never thought you can add so many particles and at the same time increase the temperature to its highest. Hey, are you fun yet? No. I don't know what else to do with this. Goodness, then I have one temporary here arranging all of the particles in a solid state formation. Right? Can I just show everyone? Remind everyone. Yeah, so remember, solid state, all the particles are arranged neatly in an orderly fashion. I never knew you could drag the particles around until today. So I was 2 years old and I realized that you can do that. Yeah, I give you about a minute more to have as much fun as you want before we discuss the observations made in this simulation. Can already, yeah. Okay, could I get everyone to stop your simulation? You put your iPad down. After this, you all can lock yourself out. And continue with the simulation if you wish. Okay, could I get you to stop for a while? We'll make sense of what you just did. Okay, thank you. So earlier on, we noticed a few things. First and foremost, I asked you to add as much thermal energy as possible. You find that the more thermal energy you added, oh wait, I might as well show you on my screen, okay? You all don't need to do a lot of MIA, you already had your fun, huh? You go crazy, okay? So, if you were to add more thermal energy, you find that, oh, the particles seem to be moving faster and faster. Why are they moving faster? Because the thermal energy is being converted to kinetic energy by these particles. They indicate over here, the more red it is, the more kinetic energy it has. You also find that, on average, if you look at the temperature also rises. The more thermal energy you add, the faster the particles go, the higher the temperature is. Do you notice that the particles here, they do not all have the same kinetic energy? Some are moving very fast, some are moving slower. You observe something interesting. I want you to follow some of the fast moving ones. Okay? Follow some of the fast moving red balls. Observe what happens when the fast moving one bumps into a slower moving one. Yeah, do you see that when the red one, the faster one, bumps into one that's slower, the slower one gains kinetic energy, it also moves faster? In this box, therefore, they are kind of just averaging the kinetic energy out, they're just sharing it among each other.
Yes.
Yeah? If, therefore, I were to stop this entire model, if I were to then start to add more particles into this system, do you realize that the more particles I add, that comes with very little kinetic energy, and if I start the system again, now they have to share the kinetic energy with even more friends. Notice that the temperature has gone down. If I were to stop the system again, I'm going to add more particles into the system. And with the same amount of kinetic energy being passed around, you find that on average, there is less kinetic energy overall. Right? With more particles I add, and with the same amount of kinetic energy, on average, now everyone has less. How can I put this into an equation? Therefore, temperature is nothing more than a measure of what is the average kinetic energy of the particles. And we observe this because if I have more particles in the system, you find that the total amount of kinetic energy needs to be shared with more particles. The temperature goes down. This makes sense mathematically speaking to you. If the bottom becomes bigger, the value will start to decrease. You all learning what math, right? Yes. Okay. So this is what we observe here. Temperature is nothing more than the average kinetic energy inside the system. If I have more particles, you find that the temperature will decrease given the same amount of kinetic energy. If I want the temperature to increase, what could I do? Okay, so if I increase this, temperature will decrease. Now a question for everyone. How could I increase the temperature instead? Which out of these two, what could I change to increase the temperature? Sorry? Okay, I guess you could do two things. Number one, if I want the overall temperature to increase, one way is to make the number on top bigger, right? I could increase the total kinetic energy. Then this temperature would increase as well. Another way is I could decrease the number of particles at the same time, and the total temperature would increase. Okay, so temperature, as this simulation is trying to show, is a measure of the average kinetic energy, or in other words, the shared kinetic energy among whatever particles is within the system, solid, liquid, or gas. That is where I would like to sort of stop today. And as you know, for temperature, there are a few units that you may have heard of. You've heard of Fahrenheit, Celsius, Kelvin. These are different forms of units for temperature. I would like everyone to try this rather interesting challenge. Okay, checkpoint 2. What do you think? Object A and B have the same mass. But object A has a higher temperature. Okay, temperature. What is temperature? Is the average kinetic energy. So, which object has a higher average? Which object has a higher total? Okay, either A or B. I'd like everyone to try now. Given that temperature is the average kinetic energy, temperature is the average kinetic energy. So if we compare both of them, object A has a higher temperature. Done 2.1, you can try 2.2. Once you're done 2.2, you can knock yourself out and add more particles into your simulation if you wish. Do 2.2 first. Okay, what is the answer? Temperature equals to average kinetic energy. So we look at this question up. If A and B have the same mass, but A has a higher temperature, which one has a higher average kinetic energy? Will also be A, because temperature is the average kinetic energy. So answer will be A. If on average all of the particles have a higher temperature, has more kinetic energy, you find that total A will also have more kinetic energy overall. Yeah? The next one. If object A and B have the same temperature, but object A has more particles, hence higher mass, which object has a higher average kinetic energy? Okay, so pay attention to the question. It says both A and B have the same temperature. Temperature is average kinetic energy. In other words, both object A and B have the same average kinetic energy. So, which one has higher? Actually, neither has higher. Both have the same average kinetic energy. In other words, both have the same temperature. Temperature is equals to average kinetic energy. So if you are still confused, go and write beside. Temperature equals average kinetic energy. They are the same thing, just a different way of saying the same thing. But which one has a higher? Which one has a higher total kinetic energy? Here will be A. But why so? Let me show you a diagram. This is B on the left, this is A on the right. Say again, this is B on the left, A on the right. Look at A, notice that on average, notice that each particle kind of have this same average kinetic energy, moving at same speed. However, notice that A has a lot more particles moving at that speed. So if we add up all the kinetic energy together of A, actually in total, we have more kinetic energy. Okay, that's why A would have the greater total kinetic energy. If you find this hard to understand, you may want to draw in two boxes to help you understand this concept. So you can draw two boxes. The first box, maybe you draw a few particles moving at a certain speed. Then you can draw another box with a lot more particles, but this time also moving at the same speed because same average kinetic energy. Okay, but in total, this has more kinetic energy in total. Okay, we have 1 more minute to the next lesson. So we'll stop here for you to consolidate whatever you like to do for your textbook to neaten things. Or you can go back to your simulation. Okay, that's all for today. Okay.